Hello, here we are. Once again, this is our last video lecture before the review session. It is the psci 168 video lecture 41. So we're going to work through generators and transformers and motors. And next time we'll have a full hour review for the final. So let's get started. I'm going to review first of all the laws of electricity and magnetism. I'll list them on the board here. Yeah. So laws of electricity and magnetism. So this is a good way to remember what's going on and all the connections that obtain here. So for electricity, we have electric charge, and we know it comes in positive and negative. And then we have some work equals Q delta V. And from there we quickly learned that power current delta V, this was really useful to us. We could apply this to all of our day-to-day electricity consumption. And I won't mention Ohm's law. Well, maybe I should also. Delta V Ri, from which we also had power equals delta V squared over R. But this is really the one we made the most use of. It's got the voltage, it's got the current, it's got the power. Good, so that's the first discussion point, the first section that we've learned about. Then we have the magnetic field, or I'll write magnets and the B field. Magnets and the magnetic field, we like to just use the letter B, it's a vector field. And we study those things, magnets, iron filings, patterns that are formed, the interaction, North Pole, South Pole, repulsion, attraction, all those things, magnets in the B field. Okay, and at that point these things are separate, not connected, but there is of course a profound connection. And we learned that the B field, so if you have a magnetic field around, it will act on a current. So acts on electric current, which we know we have the letter I for that. And since that's a B field and a current, and when I say acts on, I mean it acts on it with a force, it turns out that allows us to build an electric motor. And I have a little tiny electric motor here that I'm going to explain later on. It's one that makes everything clear. Good, so much for that. So electric motors are possible with this connection. The next law was that electric currents produce a magnetic field. So electric currents I produce magnetic fields B. That's an E right there. Magnetic fields B. I'll put them in parentheses. And well, you can get electromagnets, and it also frees you from the necessity of having magnets in any size, because once you learn how to produce magnetic fields with electric currents, you can get any kind of magnetic field you need. Good, so we have that, and then the fifth and very important law was Faraday's law. It's important enough to put the name there again. Faraday's law was that changing flux produces, so changing B flux, changing magnetic flux produces a changing voltage. Well, this is enough to generate electrical energy. So generators, on the one hand, and transformers. And we're going to look at all of these as well as we can under these circumstances. So the law number 3 right here gives us electric motors. And Faraday's law gives us generators and transformers. So we'll learn about that. And I brought some of that with me. Let's see here. So I will start with the discussion of the generator. Okay. And I have hand crank generators here. And I can even make a point right away before I explain what's inside of these things. So there's a crank on here, and I can turn the crank. And I turned this one, and this one turns. So if I do it this way, this is the generator, and that's the motor. But if I turn the red handle, this is the generator, and that's the motor. So we already see that generators and motors can be the same thing. Okay. So that's one point to be made. But yeah, so in order to talk about generators, I have to make a picture for you guys. So I'm going to erase all of this, and we'll talk about generators. And we'll actually see how these laws come into play. That's the important thing. That's what we're really trying to do here now. So the generator and I have to construct this. So we need, first of all, we need a magnetic field. And the way we're going to imagine the magnetic field is that it is coming out of the board. Remember, magnetic field has a direction. So imagine that we have magnets configured in such a way that it's coming out of the board, and these little dots with circles are like arrows that are coming at you, okay? Like arrows. So that's what these are, and this is our magnetic field. You can't see it, you can't feel it, but good. Can't draw too many of these, but a couple's good to have. So magnetic field coming out of the board. So B field out of the board. So what we now take is some wire carefully done, and imagine this is an axle, and I do several turns of wire, and then I keep going here. And what I'm going to want to do, and this is what we're talking about, wires, insulated wires, that, hey, good size. Okay. We're going to put a handle on here so that we can turn this crank. We can actually turn this, and we're going to turn it so that it turns like that. And what that does is it has a changing flux, because this is perfect now. Just hold this thing here. Okay, I prefer this one. Okay, so this is a coil. There's the wires coming out. It's on an axle, and this is the full flux flowing through the coil. When I turn it this way, there's zero flux, and when I turn it, I continue to turn it, it's the same flux but with a minus sign. So it's going to be a changing flux because the orientation is changing, okay? And I'm doing this by turning that handle there. Okay, so we'll say you turn the crank, turn the handle, and so we have a changing flux. Okay. And here's where Faraday's law comes in. Delta V was equal to N, the minus sign that we don't have to really worry about delta phi sub B over delta T. So we've got that, and let's do a little better here. So that is N number of turns minus sign equals delta V. That is a voltage. So where is that voltage? Well, what we do is we put some brushes on here and connect a wire. Okay, so the wire here doesn't twist, it's just laying on here. And yeah, now the delta V is between these two wires. If I hook up a light bulb here, it's going to glow, you know, if everything works out right. So this is a generator. And how much voltage we get depends on how many turns here. That's N is the number of turns. Remember that from last time. Number of turns, and then the change of the flux. So phi sub B is the flux flowing through here. Good. So yeah, we could put a resistor here or a motor or something, and we would actually have, say, a light come on, and if we opened a switch here, there would be nothing. And this is a really interesting feature. You open the switch and it spins very freely. You don't feel any resistance. You close the switch, you get some resistance, because you have to do the work, put it in here, in order to get that thing to glow. So I showed you one of these generators. Now let's take this one here, and I'm going to hook it up to this little motor with a propeller. Forget what is on and off. That's on. So I'm going to turn it off first. So I got a switch right there, okay? Spins very freely. So when we're all together in the class, everybody has to try this. Spins very freely. Then I flick the switch here, and suddenly I have to work. So in order to get that work done, I have to put the work in. Right? We learned conservation of energy. This is an example. I'm transforming my work, energy generation, power, over to the motor there. So that's the big convincing demonstration. Everybody should actually try this. And if you can get your hands on something like this, you're going to want to try it. If you're turning it and you turn the switch off, super easy. So that's where we are now, and that's what's inside of this little device here. Okay. Magnet, coil of wire with so and so many turns. So N is the number of turns. So you guys know volts, that's number of turns. Number of turns. Okay. And by this demonstration where I made these things work each other, you can realize that if I put a generator here, I can actually turn this into the motor. Okay, I can do both directions. But I want now to continue this picture. I hope you got room on your page. We want to build in a transformer. I couldn't find the transformer backstage here, so I have to describe it to you. So now we know we have delta V here. Okay. And a transformer is the following. There's a big iron frame. This is an iron frame. Okay. I'll even give it a little depth. Just a chunk of iron like that. And it has some depth there, okay? And what we do with this wire, by the way, this is all insulated wire. Okay, like this green insulated wire with copper in the middle. What we do is we wrap this frame, and I'm just gonna pretend I can draw wrapping it. We wrap it with n⁻⁴ turns. Insulated wire, and then on the other side, we have wire wrapped around it with n⁻² turns. These wires are not in contact with each other, but let's use blue. Same as the law here, right? We're getting changing voltage, therefore we're getting changing current. Okay, we'll close this now. Close this switch. Open one here, we don't need this resistor right now. Okay. So we're getting a changing current over here. The changing current is producing a B field. The iron core, I'll just write iron core here. This iron frame is really shaped like a frame. What it does is it actually channels the magnetic field around, so we're getting magnetic field, and there's no contact between the wires, there's no current flowing through the metal, but the magnetic field vectors I'm indicating with these arrows in both directions. We're getting a changing flux here, we're getting a changing flux over here. So without any contact, we have delta V1 over here. What color we want to use for that? How about red? We have delta V1, and over here now we get delta V2. And I'll just give you the law of the transformer. Let's call it, so this is a transformer. Only got one board today. And actually, before I give you the law of the transformer, those little square boxes, little cubical boxes that are on a plug when you have a little device, okay? If you have one that you're ready to get rid of, save it and cut it open sometime. You will actually find a little iron frame inside of it with wires wrapped around it, okay? Don't take my word for it, cut one open. Okay. The little boxes on a plug in for your devices. So the law of the transformer, let's just call it that, is this. Delta V1 divided by N1 is equal to delta V2 divided by N2. Now what this means is, this is just a ratio, but let's just solve it for delta V2. Delta V2, that's the voltage that you get. Say you put in 120, okay? Question is, what do you get out here? And that is, I'm just solving for this, that's the ratio of the turns times delta V1. So let's take a moment just to ponder this. Make sure you have a lot of room on your page when you write this down. So suppose this is 120. And N2 over N1 is 1/10, right? So this side has 10 times as many turns as this side. Then 120, back up. Delta V1 is my 120. Okay, this is delta V1. I have 120, but if I have 1/10 as many turns on the right side as the left side, then I'm going to go from 120 down to 12. Okay, it'll be a step down transformer. That's what your little devices at home often have. They go from 120 down to 12. And the other way around, if you took your little transformer and reversed the direction of it, you could go from 120 up to 1,200. Okay, you get a high voltage or a low voltage. And high voltage is good for energy transmission. It's efficient. Low voltage is safer. Okay. So I'm just going to give you a couple vocabularies here. Transformers, there are step up A step up transformer increases the voltage and a step down decreases it. So yeah, you can look something up about those. And what's interesting also is the transformer, which is such a simple thing, it's an iron frame with wire around it. It depends on Faraday's law. You can't do a transformer of this type with a battery. A battery is a direct current. This produces an alternating current. So yeah, I should have noted that. This is alternating voltage and current. Alternating voltage and current. Yeah, so there we go. There's our electrical engineering. We just have magnets, we have wire, we have to turn a handle that produces the alternating voltage or current. We can run devices with alternating voltage and current. If we have to step up the voltage or step it down, go through a transformer. Transformer is using the same law that's being used over here. Okay, generator, transformer, step up, step down, and I'm going to finish up by showing you a motor. Let's see how we're doing time-wise here. Okay, good. Okay. So then I'm going to show you this little motor close up. And that should actually cover what we need to know. Yeah. This is the kind of thing you can also find other diagrams. But I don't think they're going to be more transparent than what I showed you. But if you can find good images for this stuff online, by all means, put them in your notes. It's the Faraday effect over here. Alternating current, voltage, current. Faraday effect here gives us the alternating flux in this coil. The iron core brings it over to this side without any current touching or anything. And Faraday's law here, once again, gives us delta D2. So you can see that Faraday's law is so important. Oh yeah, let me say one more thing. So what about hydroelectric power generation? That's the water going through the penstock that is turning the handle, so to speak. Okay. And it's spinning very freely until a load is applied to it. So we can imagine these gigantic coils are spinning. There are magnets. Everything is just scaled up immeasurably. Then somewhere over here, you turn on a light, or you ride the elevator, or you do any of the many things that you use electricity for, and then, so this is, this could be 100 miles away, then this device feels that resistance. It's the same as when I turned on the switch on this propeller. It's spinning freely, and you turn on the switch, and you feel that resistance. Okay. So that's what's happening on the scale that we've been talking about all this time. We finally are seeing what's going on. We've got magnets and wire and coils and everything, and all the way downstream to here. So yeah, I encourage you to pursue this a little more, see what you can find. As far as transparently seeing what's going on, you've got it right here. Okay, I'm going to tell you a little bit about this motor here, and then I'll hold it up to the camera. You may be inspired to build one yourself. Okay. So this is going to be a direct current battery driven motor. And the ingredients are just a loop of insulated, it's lacquered wire. So it's lacquered wire, so it's insulated, copper on the inside, very thin insulation. And you actually just wrap it around a C-cell battery and wrap things, let two ends stick out so that this is its own axle. It's a C-cell battery and some copper framing there, and then some magnets. Okay. So I'm going to describe how that works, and then I'll hold it up to the camera. Okay, what are you going to call this? Direct current electric motor. This is a C-cell battery electric motor. Okay. So we need this coil. I'm going to draw it from the side. It's got a bunch of turns, and you wrap the wire around, it comes out there. So that's what that is, okay? Copper wire coil. And as it's facing us like this, you're going to scrape off some of the insulation so that you have bare copper on one side, like say the bottom side of this. So you scrape off the copper on one side. I'll hold that up to the camera too. Now underneath this thing, and this is actually, for the moment, this is the orientation. Underneath this thing we have a magnet, and I'm just gonna say north-south. These are these flat magnets I have right there. But the point is, the magnet has a magnetic field that's going like that, okay? B field. And if I connect this now to a wire, there's a wire, and over here we're going to have battery, delta V. Then of course I have a current. And the way I've done it here, the plus and minus side, I have a current going here, current going there. And I'm going to indicate the current. Since the red is the bare conductor, let's indicate the current with blue. The current as it goes, well, can't do that. We're gonna have to use black. So the current is clockwise. Okay, it's many turns, but the current here is clockwise. And now this law of a B field, go ahead and write B here. A B field acts on an electric current, and it actually produces a torque. The thing's going to want to spin, and when it spins a half a turn, the conductor is no longer in contact, and the current stops flowing, and the spin just completes the turn, and then it kicks in again. Okay. So that's basically the motor. Magnet produces a magnetic field. Here's the loop of wire powered by that battery down there. Okay, so wish me luck. I'll hold some of this up to the camera in a moment, if we can. But for the moment, it's on its axle here, and you can spin it, but it's not going to spin forever. Okay, it's going to stop. If I drop a magnet in here, and it spins like a little motor. Okay. Now you know what you want for Christmas. So I'm going to hold that up and just see if I can put this over here. See if I can indicate it there. Let's see how close we can get here. Well, here we go. let's see if I can, oh yeah. So this would be, oh, there we go. This would be the turns, and you can see there's the shiny side. Yeah, that's where it's been scraped off. And there's the side where it hasn't been scraped off. Just like my picture on the board. Not scraped off, shiny side, been scraped off. There you go. Okay. Now, once again, okay. No magnet. Okay. I'll put 2 magnets in this time. Get in there. And now it's turning. There we go. Okay, yeah, that reversal of spinning, that has to do with the video camera. It's actually spinning in one direction. Okay, like I said, now you know what you want for Christmas. There's the motor. Okay, I'm just going to finish up with a couple of points. When you have some device like this, and a couple of years ago with a different class, I had 15 students. We made one for everybody. Okay, this thing here, you actually take it apart and put it in a little plastic bag. There we go. But you can actually, if you have it in front of you, you can actually feel the force. You can feel the torque. You can feel it trying to turn ever so slightly. It's a weak force, but you can feel it. You can also impose a magnetic field on it and make it stop in reverse direction. Everything we've discussed, you can actually feel and see happening on this thing. For example, if I were to take this out here, 2 wires and a little electric bulb, of course, I could make the electric bulb glow. You know you have a current there. Okay, be that as it may, this kind of device is completely transparent. All the laws are, you can line up each law that we had on our list and actually feel it and see it happening. This device, everything's enclosed. You're really not seeing, it functions, but you don't really know the principle. So here you know the principle, and that's what I'm going to end with. Okay. So next lecture will, just be 1 more hour, and I'll review everything for the exam. So the midterm went well, and the final will go just as well. And I'll give you a heads up on what the topics will be, and so we have nothing to worry about. Okay. So until then, maybe see if you can pull one of these out of a hat, and I'll see you next time.